All right, so I'm going to shift into human factors, interaction with AV, and perhaps I'm going to start with the variability and the approaches, safety approaches in particular with OEMs from multi-layered safety to vision-only systems, as it can be seen in the picture. Tesla is using now only cameras, no LiDAR, no ultrasonic sensors. It's only now for hardware 9 cameras versus more than 40 different sensors from Waymo, as an example. These variations affect sensing, software and hardware update frequency, and driver interaction with such evolving systems. While infrastructure must adapt to mixed system reliability and performance, our NCHRP simulator studies assess how drivers interacted with level 2 and level 3 automation for certain scenarios. Findings will guide infrastructure designs that enhance safety, trust, and consistency. Next slide. Another reason why human factors are also critical and needed, looking at recent data and investigations by the National Highway Traffic Safety Administration over the past year and this year, reveal also the critical human factors element in researching how human drivers and human users are interacting with automated vehicles. Open probes now cover millions of vehicles due to automation errors in fog, glare, and other challenging conditions. Waymo, for instance, issued a recall to correct barrier detection software. Tesla investigations also raised concerns about delayed crash reporting and rule-violating behaviors like red light and stop sign running and lane incursions. These real-world issues emphasize the need to understand how drivers and automation interact and how infrastructure can help reduce such risks. Our UC field testing, as demonstrated by Munir, utilizing FSD 12, version 12 and hardware 3. We also extended this work, and we did about 1,600 miles of drive utilizing the recent publicly available FSD 13.2.9 with hardware 4. This has basically revealed more issues, even there are some improvements, but generally speaking, when we think about FSD in particular, and we can identify different issues, including like FSD from park, illogical navigation out of parking lots, illegal U-turn sometimes, maximum speed offset that actually recommended by Tesla itself to be plus 40% above speed limit just to match traffic flow. Sometimes, yes, we understand speed variability is a big issue in traffic safety, but going up to 40% above the speed limit, Tesla FSD right now for this recent software update is speeding most of the time, specifically when you think about the different full self-driving modes. In hurry mode specifically, you can see that Tesla is always occupying the most left lane, and it does multiple lane changes in that particular mode with a lot of speedings as well. I'm not going to go over the different issues that we have experienced with our observations from the field testing. You can go to the next slide, but I'm going to just highlight some of these specifically related to work zone, as mentioned by Sam and by Munir, and the complexity and difficulty of detection of work zone and the complexity of the faded lane marking, among other issues, including work zone flaggers and ramp metering signals that actually FSD right now is not reacting or responding to. It is critical than ever before to understand how human drivers are utilizing level 2 and level 3 automation between autopilot, which somehow considered level 2, and FSD, which is considered level 3 automation. And also, we're keeping our eyes on the improvement with the recent release, and it's still, I think, in a beta version 14.1 that was released a couple of weeks ago. It is only available right now for influencers and early testers. We don't have access to it right now, but Tesla is promising that this is going to enhance handling closures, debris, work zones, potholes, and emergency vehicles as well. So this particular case study utilizing our UC driving simulator lab is focusing mainly on one case study that was identified by the NCHRP panelists to look specifically into work zones with flaggers in suburban environment on a two-way highway with one lane closed. Again, we have these lists. Our recent publication paper published in Accident Analysis and Prevention this year also indicated that AVs, these results actually is based on 27 AV testers in California. These data from DMV, California DMV between 2021 and 2023. What we found is object perception, detection, and prediction issues accounted for 46% of this engagement. Additional and other studies, in addition to our UC initial results and observations from the field study, also showed a wide spectrum between people trusting automated systems versus driving in a very conservative fashion when it comes to using FSD among other systems. This is also according to a recent study utilizing an online survey for 103 Tesla FSD users. So the objective of this case study specifically is to understand and to, if you can go back to previous one, to understand how automation disengagement can guide infrastructure owners and operators and OEMs to improve safety of ADS. Here, this is one of the recent FSD 13.2.9 hardware 4 in a construction zone. There are two issues here. First, it selected the most right lane, the right turn lane to go straight, and after actually approaching the intersection and the signal, it tried to squeeze back in full self-driving. I would have disengaged early on if that it was not actually for this particular study, but I waited to see how FSD 13.2.9 can actually react and correct for such violation to start with by selecting the wrong lane from the beginning at the work zone. Next slide. Here, specifically related to our case study, we can see the progression that FSD has made from version 11, which usually FSD actually reacted to a flagger with a stop sign as if it is an stop sign at an intersection. So it will wait just like for a few seconds and it will continue regardless there is someone is holding the sign in the middle of the road. This was actually improved in version 12. And in this particular one, Tesla disengaged the full self-driving when it saw the stop sign. But after that, the driver tried to re-engage. And actually, Tesla was trying to make multiple attempts to continue behind the flagger once it was switched to slow. However, it did not happen until it was actually switched to slow. Another video on the right is showing this engagement, again, responding to a construction zone flagger. However, in the recent FSD version, the FSD system did not recognize the slow and it did not continue, and the driver had to take over the driving manually. Next slide. Another very interesting interaction with a flagger at the work zone. Tesla made a right turn here, and actually it just overtook cars waiting for the flagger with a stop sign, and the driver had to back behind these cars again. But the car actually detected the stop sign and stopped. Next slide. So the main task of this one is to see how infrastructure modification digitally and physically could actually improve and enhance the engagement and disengagement early on prior to work zone with a flagger with a stop sign. Next slide. In our case study one, we designed 18 distinct scenarios. We had baseline testing level 2 and level 3 without takeover requests. This was actually introduced in clear and moderate rain. And also, it has a misinterpretation scenario where Tesla approached the flagger and then it continued as if it misinterpreted the stop sign with the flagger. And then we have the infrastructure modifications, again for level 2 automation and level 3 with physical and digital infrastructure modifications. Next slide. These are the different roadway scenes that we designed. We designed 2 scenes, 2 tangents, one on a straight segment, and another one is a straight segment post horizontal curve. This is for learning effect to randomize the different scenarios for level 2 and level 3 automation. So again, the baseline, we had no modification. We did not have any additional signs digitally or physically other than what was actually provided in the NUTCD. And then we had 2 different, 3 in general modifications. Modification number 1 was physical road sign placed at 200 feet upstream of the first work zone sign. Physical road sign 350 feet upstream of first work zone sign. And then we have digital in-vehicle message that was placed similar to modification number 1 with a physical road side sign at 200 feet, because we usually, when we have an in-vehicle warning, this doesn't need to be like far away from the critical zone that we would like to provide a warning for. Next slide. So this is a much bigger picture just to see. We introduced this physical sign saying work zone, no automation. So basically, we're trying to encourage drivers to turn off their or disengage their full self-driving or autopilot or level 2 and level 3 automation early on prior to the work zone, in case that they were distracted with a secondary driving task, by testing physical sign one time and testing a HUD or a head-up display work zone, no automation another time. Next slide. We started this experiment by inviting 7 subject matter experts. Those are transportation professionals with some experience with automated vehicles at level 2 and level 3. They provided some input and feedback to update those scenarios for the driving. Next slide. This is the invitation, and I'd like here just to touch on one aspect for the inclusion criteria, generally speaking. One of those inclusion criteria was we need drivers, obviously, with prior basic familiarity with adaptive cruise control, partial automation. We invited 15 participants in total so far for case study 1. We invited additional participants. They are not included in the results for this presentation. However, later, after the rapid evolution of the FSD, and we've seen like a lot of users now and subscribers for FSD based on like crowdsource and X and some data from Tesla specifically, that FSD is getting much better now and there are more subscribers. We decided to update the inclusion criterion for the cruise control, adaptive cruise control, and L2 partial automation experience to only include Tesla drivers with full self-driving active subscription and experience. Next slide. For our study, we started obviously by introducing the driving simulator to our participants. We also did some eye tracking gaze calibration. We had multiple warm-up scenarios, and then we started the actual experiment with for L2 and L3. Again, it was randomized for the learning effect, with and without the infrastructure, digitally and physical infrastructure modifications. Next slide. This is just an example of one of the participants driving an L2 with M1 scenario where the sign was located at 200 feet prior to the work zone first sign. And as you can see, this could be actually engaged by just using the steering wheel buttons to engage level 2 automation, which mainly adaptive cruise control and lane centering. And we can see the engagement of the system at the beginning and then the disengagement breaking when the sign was actually seen. And we see the re-engagement after the work zone and the flagger as well. We can see the re-engagement again, the participant actually re-engaged by pressing the button one more time after the work zone. Next slide. This shows the other way for autopilot. We have a dedicated button for autopilot, similar to what FSD in a Tesla or other cars that you can actually initiate. This is a supervised, hands-free. So drivers, we've seen both. Some drivers actually had their hands on the steering wheel, but mostly we had other participants with their hands actually on their lap, not on the steering wheel, and they engaged and disengaged, but the majority disengaged, as I'm going to show in a later slide, and then the engagement happened after the work zone. Next slide. So this is just the demographics for our 13 participants for case study number 1. The majority were between 25 and 34 years old, and male-dominated participation. And as I mentioned, we used both the sim observer data collected related to lane position keeping and those speed profiles, in particular engagement, disengagements, events, as well as some eye tracking data, gaze allocation specifically of the different area of interest. Next slide. So this figure specifically is showing level 2 automation with this engagement. And as you can see, it varied. We're providing here the min and max when this engagement, manual disengagement happened for baseline scenario and the center line type, digital modification in blue line, and physical modification green, and physical modification 2 with the sign at 350 feet away from the first work zone sign in purple. You can see that the best performance basically, or the maximum distance, or we can say the early disengagement, manual disengagement event happened when they have seen the sign for work zone, no automation. So some of the driver decided early on just to manually disengage. I would say that 100% for all drivers disengaged manually prior to the actual work zone and where the flagger is. But you can see clearly in this that with the infrastructure modification physically and digitally, we had the earlier and more advanced disengagements happened during or for those infrastructure modifications. And for the baseline, it's usually happened at the very late at the work zone prior to the flagger themselves. And we can see also the re-engagement happened as it was seen in the video after the work zone itself. And here, this actually is showing the eye tracking gaze data specifically. The concentration means where during those engagement, disengagement, where drivers were actually looking. And we can see in the baseline, it's somehow scattered between the roadway and the side of the roadway. We can see also for physical modification 1 and 2, where there were more of these signs on the right. There are also some gaze between the roadway itself, the center of the center channel, and the side of the roadway. There are some glances to the side of the roadway, which is expected. However, for the HUD specifically, the digital modification, we can see the majority of the concentration of the gaze is in the roadway, where also the head-up display with the warning message came on the screen. Next slide. This is for level 3 automation, and we can see perhaps a distinct difference between L2 and L3, and this is perhaps could be related to the expectation of L2 and L3. Next slide, yes. We can see concentrated clusters for the min and max. So basically, this is telling us that participants split into 2 major categories: those early disengagements, adopters, where they actually decided just to disengage the system early on once they saw the digital or the physical infrastructure modification with the sign asking them for no automation. And then we see another group of participants where they decided just to do it later when they saw also the flagger sign and just prior to the work zone itself, the active work zone area. We can also see here that digital modification in both L2 and L3, we had this abrupt response to the warning when it came, because the modality used for this was both visual and audible. And that's why it triggered more abrupt response to disengage and brake. And this is actually is noticeable in the speed profiles for the different infrastructure modifications presented on this slide. Next slide. Very similar for the gaze was also expected, and we got a very similar results for the gaze concentration and glances on the physical and digital infrastructure modifications. And mostly the difference here were statistically insignificant when it comes to adding this, which basically can tell us that we did not introduce additional distraction by providing either the physical or the digital infrastructure modifications. Next slide. We followed this by a post-survey where we asked questions with respect to the cognitive workload, and as expected, the level 3 had the lowest cognitive workload on drivers while driving this particular one. As expected, some of them actually expected that level 3 can perhaps handle work zone to some extent, but obviously for level 2, everyone understood that the car cannot actually handle work zones in particular, and they would need to just disengage the system prior to the work zone. The comfort also, we can see that the comfort for physical and digital infrastructure, the comfort and familiarity with the physical infrastructure modification, the added sign or the new introduced sign received 7 out of 10 versus digital just received a moderate, which basically 5 out of 10. Also, as part of an open-ended question in the post-survey, 77% of the participants preferred the more familiar road sign on the side of the roadway, not the in-vehicle message. They also complained a little bit about it was a little bit abrupt with the audible and visual. This could be also improved, but this is out of our hand. This is going to be done by infrastructure to vehicle communication, and the modality could be actually tuned by the OEMs themselves. Next slide. I'd like here just to touch a little bit on the latest beta version of FSD 14.1 with hardware 4. As you can see in this one, the performance has improved quite a bit. You can see in this scenario specifically, the FSD system detected the stop sign and also the slow, and seamlessly the FSD system moved or converted from like slowing down, approaching the stop sign, and upon or the onset of the showing the slow sign, even though it was not actually provided in the visual display on the car itself, it still showed a stop sign. The car continued and increased the speed, and it changed lane to the opposite direction. Next slide. We have another example here with 2 flaggers basically in this one. And as you can see, in the first one, it was detected as a stop sign. The car reduced the speed almost to 0. It's close to 3 miles per hour, but it's almost, you can see it's almost 0. And then once it's switched to slow, the car actually started right away, seamlessly moving to the opposite direction and continue and increasing the speed. And now you can see actually another flagger with a slow speed, even though it's going to be shown as stop, it's not stop, it's slow if you look up on the video. And the car actually continued through while seeing the flagger with. So there is actually a very significant improvement when it comes to dealing with flagger. However, before I actually go through the conclusion for the case study 1, I'd like just to highlight why this is still needed. I'd like just to touch on with not only the variability in the system and the rapid evolution of those FSD systems. I'd like to mention that not every single FSD subscribers or owners, because there are 2 models. You can either purchase the FSD from the very beginning, or you can subscribe to it. We will see still a lot of variability and variation between FSD systems on our roadways. I'd like to mention that older Teslas with FSD hardware 3 specifically and prior hardware will not be able to receive those newer updates. So 14.1 is not going to be released for everyone. This is only for hardware 4 with the 9 cameras and no ultrasonic sensors, among other sensors. So basically, what we can tell here from FSD version 11, 12, 13, and 14, we will see all of these different subscribers. Yes, we understand that not all of them will see more subscribers and users for recent releases, because actually it improved quite a bit than what we're going to see for older hardware and software versions. But still, this wide variability between those different safety approaches when it comes to strategies, when it comes to FSD implementation, we can see that we still need those infrastructure digitally and physically to communicate with users of those level 2 and level 3 automation as well. So with this, the conclusion here, we can see that both physical and digital modifications improve driver awareness about those flaggers and work zones in particular, and their takeover was much earlier than the baseline with no physical or digital infrastructure modifications. The physical infrastructure modification with 300 feet sign away from the first sign at the work zone had the earliest braking onset, longest braking distance, smoothest deceleration disengagement in both automation modes, L2 and L3. Next slide. When it comes to visual attention, as I mentioned, we don't have any surprising results from this. Actually, both digital and physical infrastructure modification did not add any additional distraction to drivers using L2 and L3 automation. And as mentioned, 77% preferred physical signs due to familiarity with the sign. Our second case study is focusing mainly on interaction between vulnerable road users, bicyclists in particular, and AV. And I'm not going through the statistics provided on this screen, but I'm going just to highlight one thing, that cyclists, it works both ways, from the AV user perspective as well as from cyclist perspective. Various studies actually showing low trust in sharing lanes with an AV, and some studies actually suggested that there should be some communication that AV can relate to those users, that there's an AV, yes, I see you in the roadway, I'm reacting and I'm giving you more space, and vice versa also. AV users should be notified by the infrastructure about the presence of pedestrian and bicyclists on the roadway, which I2V and V2X could also be used for those such communication. And this particular case study is focusing on this particular aspect. Next slide. While we can also see that Waymo and Tesla recently passed the vulnerable road user interaction test with 89% according to IIHS, and then the model of Waymo actually stating that injury crash reductions versus humans, the comparison between human drivers and their system resulted in about 92% in reduction in pedestrian crashes and interaction or critical safety events, and 82% for cyclists. And I do have some also videos about how Tesla, next slide, is reacting to bicyclists, detecting them very early on. You can see the bicyclist before on the screen, before even on, you can see it from the windshield. You will see also that the recent 14.1, the beta version available only for testers, early testers, you can see it's given more space even in a very narrow roadway with no marking, and Tesla's giving more space. We have another example, next slide, showing also another roadway type with no shoulder, that Tesla is actually crossed over the center line just to give more space to the bicyclist. Next slide. Another example here, and more like suburban settings, you can see it's very crowded. We have parked cars on the side, no space for bicyclists. Tesla's navigating between the giving more space to the bicyclist while also making sure that it's giving more enough space for the oncoming traffic. So it seems like there are a lot of improvements. However, we still would like to assess from both, and again, for older systems and for both our AV users as well as from bicyclist perspective. This is where we're actually going with the second case study, driving simulator study. Next slide. And here I'm just listing additional statistics about the fatalities related or involving vulnerable road users, which account for about 50%. And the coexist, which basically are different road users and different types of manual driven as well as automated vehicles with different automation levels will coexist on our roadways in the mid-term and like the immediate term and mid-term and long-term. Perhaps we can see maybe a little bit of a shift in market penetration rate when it comes to adoption of AV system and the readiness of our infrastructure. What we aim for this particular study is to see the different types of infrastructure modification while we can provide those communication between AVs and bicyclists, as well as the physical separation between bicyclists and AV or vehicles, generally speaking. Next slide. These are the tasks, very similar to the first case study. This is an ongoing, so I don't have a lot of results to share with you today. Next slide. But these are the 3 different environments designed so far, and we started testing with some participants. Again, this is only level 3. We're not going to focus on level 2. This is only for Tesla FSD subscribers and active subscribers for full self-driving for Tesla in particular, where again, this testing both the infrastructure modification, shared lane, a bike lane, a conventional bike lane, as well as a bike lane with a physical vertical separation, in addition to digital communication between bicyclist and AV as well. Next slide. We do have an online survey that we're also conducting, and I'd like any Tesla drivers on this call or this webinar to go and scan this QR, and also the link is provided in the chat box to take this online survey with respect to issues and how FSD your system and how actually you're utilizing the system for both these case studies for work zone with flaggers. There are some general questions at the beginning, but we have a focus also to complement the 2 case studies for work zones as well as the interaction with vulnerable road users. With this, I'm going to turn the presentation, the webinar, to Sam. Thank you, everyone.
I feel like we have a couple great questions that we're going to want to let people know. We are at the time block, but if we can take just a moment to go through the ones that were answered previously. If you have any additional questions, please put them in the Q&A box, and we'll look forward to doing that. And again, what was presented on will be recorded, and so that you can share with everybody. So real quickly, if you could just address, Samantha, how agencies might measure or monitor infrastructure condition to optimize performance, and the recommendations that that was asked about, and what your reply was.
Yeah, so in that TRB web resource, we are currently working on developing an implementation strategies section, which will be in another tab. And essentially that's more so like deployment strategies for IOOs. And so one of the sections that will be in there is essentially on conducting infrastructure readiness assessments. So I know that there are a lot of different vendors in this space which will recognize in that document, but one that just comes to mind, like I highlighted in the chat, is ESI AI. So they're an online app platform that can allow IOOs to monitor and assess their infrastructure themselves.
Thank you. Yeah, and that's the mention of ESI. Just remind everybody is FYI only, not a recommendation by the project or by anybody else, but that's great. Thank you for that. And then Dr. Nizal answered a question that was in there about were any other vehicles used other than Tesla or the Tesla FSD for rail crossings? And Dr. Nizal, if you want to make sure everybody, people haven't seen that answer, if you could go ahead.
Yeah, so for the NCHRP, we were looking really at the most commonly used production level vehicle with a full self-driving basically capability. And at the current time, it was Tesla. This doesn't mean that we have others, but the one that is currently most used, I would say, is basically the Tesla. And one important thing that I would say that those recommendations as will be are important really for the level 2 and level 3, and we are aware, as Dr. Ahmed have mentioned, that there are new versions of the full self-driving even for the Tesla, but those might not be applicable for basically older version of those AVs. So our focus is really for current and maybe near future. Again, things might change, and that might really why I think there will be a recommendation that all those like whatever we have in this study might need to be re-evaluated maybe in 5 years. But again, the thing is, we wanted what is currently common practice, and that's what will be applicable really in the currently and in the near future. So yeah.
And that serves as a good reminder for the links in the chat box for assisting, for whether you're a Tesla owner or want to contribute and give response back. And I thought that the four of you did a great job describing how you actually capture a rapidly changing environment like that. So just for those who maybe didn't see the beginning of the webinar, make sure to go back and look at some of the research frameworks and approach on how not only the environment has changed rapidly on a month-to-month basis through the last year, but the approach for the research project to capture it.